All right, everybody. We are starting to wind up our examination of matrices, and we're going to look at this topic, inverse of a square matrix. All right, so the first thing we need to know about that is there are certain things that we call an identity. Okay, so for instance, I need a little definition here first. So there's an identity. And you actually probably already know a lot about identities because you know that if I have 5 plus and I want some number there and I want to get the 5 right back as the answer, there's some number that I can add there that will, give me back the number that I had. What is it? 0. Yes, the number is 0. Okay. 5 plus 0 gives me 5. And in that case, it's called an additive identity. Okay. Additive because we are adding. That is the operation right here. Plus, right? And identity because I like to think when I look in the mirror, I can identify with myself. I can see myself and what I think my identity is. It's like a reflection coming back at me, right? So whatever I do here, after I add some number, it reflects back to me that same number. So that's an identity. Okay. So in this case, 0 is the additive identity whenever I'm dealing with, like, say, I had natural numbers or integers or something like that. We all know if we add 0, it doesn't change the value, right? Okay. We also know about multiplication. 5 times some number gives me back 5. Okay. And that would be called a multiplicative. I know you don't have to know multiplicative, you just have to know multiplication, right? Multiplicative identity, that's what this guy is. And 5 times some number gives me back the 5. Again, I see this reflection going on where my answer is the same as what I started with. So what would that be? 5 times 1. 5 times 1, Dr. Webster. That's right. Okay, so for most of our lives, we have dealt with stuff like this. If we add a 0 to a number, it doesn't change its value. If I multiply a number times 1, it doesn't change its value. Okay, the problem that we're going to have with this identity thing is that for matrices, it looks a little bit different, right? Because I don't just have one number plus one number, I have a 2 by 2, for instance, or I have a 3 by 3. Okay. And remember, 2 by 2 means 2 rows and 2 columns, and 3 by 3 means 3 rows and 3 columns, right? So we've got those um, dimensions that we can talk about. Okay. And actually, what you don't know is I've already secretly had you working with an identity. You just didn't know it. Okay. I snuck it in on you. Okay. So the 2 by 2, the identity matrix is 1 0 0 1. Okay. And that was what we would do whenever we had an augmented matrix and we had the solutions out here, right? I wanted you to get that 1001 plus some numbers out here when we were solving systems of equations, right? Okay. In matrix world, that is the 2 by 2 identity. Okay. So what we're going to see is whenever I go to multiply this guy through, for multiplication. Sorry. So what we're going to see is when I go to multiply some 2 by 2 matrix by 1001, I am going to get reflected back to me the original matrix. Okay, so that's what happens whenever I'm dealing with identities. We'll see one of those in just a second. Okay, and then what do you think for this 3 by 3 guy? What's the multiplicative identity? And notice, if you will, that I skipped additive identity for matrices because that's just basically boring. Okay. If I wanted to add something to a matrix and get the same thing back, I'd have to add all zeros, right? And That's just not something I want to do. Okay, but knowing that this guy that I've got 1001, that is the 2 by 2 multiplicative identity. Hopefully over here you're thinking, oh, I bet I know what this guy looks like for the 3 by 3. It's a 1, 0, 0. And then what's this second column, or sorry, second row going to look like? Well, 0 and the 1 and the 0, right? And then the third row looks like 0, 0, 1. So remember, we've already been playing with these things because we've already said, oh, we'll get this diagonal to be ones, right? And then above and below will be zeros. And here for the 3 by 3, ones on the diagonal, that long diagonal through the middle, and then zeros in the triangle below and zeros in the triangle below. We've already played with those because that's what I made us do whenever we were doing reduced row echelon form to solve a system of equations, right? It's just that we had that augmented matrix. So we had the numbers, the solutions out here beside it. Okay. So we've actually already seen those. These are the identity matrices. That's not actually what I'm after. Okay. So if you'll go back, remember I said we're going to talk about inverses of a square matrix. Okay. Square meaning that the dimensions for the rows are the same as the dimension for the columns, right? So both of these that I've given you here, let's start there. This is a 2 by 2. That's a square matrix. And this is a 3 by 3. So it's a square matrix because the dimensions are the same. Okay. 2 rows, 2 columns, 3 rows, 3 columns. Okay. So first of all, I have to start with an identity. That idea of whenever I do to this thing, I'm going to end up getting that reflection back. Okay. So we need that idea. But then we have to talk about inverses. Okay, so I've talked about identities. Let me talk about inverses for just a minute. So what's an inverse? We need to get another little definition here. We got identity, we got inverse. Okay, well, for addition, let's go back to my 5 plus. Okay. For addition, we know that what we're looking for is we're going to add some number to the 5 and it's going to give me back the identity, which was 0, right? 5 plus 0 is 5. That's the identity is 0. And so I would add something to this 5 to get back the 0. Well, what can I add to 5 to get a 0? It would have to be a -5, right? Okay, 5 plus -5, those will reduce out and give me a 0. Okay, so that would again be the additive inverse. And again, you've probably been doing a lot of this stuff for a long time with regular whole numbers and stuff like that. In this case, for adding, it's the same number, but we just put an opposite sign. So negative whatever. So change the sign. That's what we would normally do, right? Okay, so this is not important to our current thing that we're doing. I'm just making sure everybody knows like the idea first before we get into it. Okay. So what do you think if that's what happens when I'm adding, I get back the 0, what do you think happens when I'm multiplying? I need to multiply the 5 by something to get back the 1, right? Does that make sense? So I'm saying 5 times some number will give me back the 1, which in this case, the 1 is the multiplicative identity, right? So this will be the multiplicative, such a long word, inverse whenever I get it. Okay. So again, what would I multiply times the 5 to get back a 1? Well, in this case, it's really 5 over 1. I'm going to think in terms of fractions, 5 over 1. And if I wanted to get the 5 down to just a 1, I would multiply by 1/5. Is that okay? Those would go away, the 5 and the 5. 1 times 1, 1 times 1. Yeah, that makes sense. Okay. So in this case, the multiplicative inverse is we would flip it. Okay. Or we call that a reciprocal, right? If I had, for instance, let me give you a different example, 1/3 and I wanted to multiply it by something to give me back a 1, well, I would flip it, right? 3 over 1 or just a 3, okay? So it's just the reciprocal is what we call it, okay? I'm going to say 1 over whatever my number is or reciprocal. That's the idea there, okay? So again, you've probably done stuff like this. In fact, we've done stuff like this in the class because when we go to solve an equation, if I have a plus 5 and I want to get rid of that 5, I would subtract 5 and that zeroes out, right? Okay, so we've done this kind of stuff, but again, not with a matrix. Okay, so let's go back to the idea though. And again, we're going to ignore addition. That's just I like to give addition because that's a topic that most people know. Okay. But let's go back to this idea. We have some number times the inverse gives me back the identity. Does that make sense? Some number times the inverse gives me back the identity. Okay. That's what we had. But here we know the identity is going to be 1001. Okay. Inverse gives me back the identity. Okay. So, we're going to end up, what we're going to do is we're going to be finding the inverse. We'll normally be given this original matrix, right? We'll know what it is whenever we get there. And I'll make this more formal as we go around along, but I just want you to know the process is going to be the same as it was for like whole numbers here. The matrix times the inverse gives me the identity, and I'll come back to this in a little bit. But the process is the same, but it's going to look different because I'm dealing with matrices, right? Okay. And everything looks a little bit different with matrices. So I'll come back to this. First, let's just take a look at identities, okay? And we're going to make sure we know how this works, okay? So, um, whenever, let's see, identity times the matrix is going to be the same as the matrix times the identity. And what did we just say? When I multiply by an identity, it's the same as looking in a mirror. I'm going to be reflected back the original matrix. Okay. So there is a shorthand for that, but I wanted to give it to you like that first so that we can see. Okay. And notice that, by the way, I'm flipping this. Okay. I can do it either way I want to, identity times matrix, or I can do matrix times identity. What that means is the order is not going to matter here. And the reason I can do it is because these are going to be square matrices. Square matrices. Okay. Remember when we did multiplication the other day? If I had a 2 by 3 and I wanted to multiply it by a 3 by 2, that was fine. But, well, this one's not. By a 3 by 4, let's say. That's fine. But if I switch them 3 by 4 and I want to multiply that by 2 by 3, those numbers don't match like they did before, right? Okay, so order matters. Okay, sometimes I can't even do it whenever do the multiplication if I switch the order. But in this case, it's going to be okay because these are square matrices. So for instance, I'm going to have a 2 by 2. And when I have a 2 by 2, I'm going to multiply it by this 2 by 2 square identity matrix, right? What if I had a 3 by 3? I'm not going to use this guy, right? If I have a 3 by 3, I'm going to multiply him by this square identity matrix. Okay. So it depends on which size I'm doing, but they're all going to be squares in this case. And if they're not squares, guess what? You can't do it. So you're going to be like, oh, can't do that one. And that actually makes life a lot easier for us. So let's see what we got here. All right. Here's some examples. Multiply 1001 times 5304. Okay, so this is a good opportunity to practice our multiplication to practice our multiplication of matrices and make sure we all got it okay. So let's see what we got. And by the way, this is a 2 by 2 and this is a 2 by 2. These two middle numbers do match, so I can do this math. Always check first. And my answer is going to be a 2 by 2, right? So let's see if we remember how to do this. We just did it the last video, right? So what do I have in the first row, first column? 1 times 5 is 5, plus 0 times 0 is 0. 5, right? Okay. First row, second column. 1 times 3 is 3. 0 times 4 is 0. 3 plus 0 is 3. Okay. How about second row, first column, these guys. 0 times 5 is 0, plus 1 times 0 is 0. I think that's a 0. Second row, second column. Cover up the one that we don't want anymore. 0 times 3 is 0, plus 1 times 4 is 4. 0 plus 4 is 4. Okay. So there we go. This guy is our inverse. I'm sorry. This guy is my original matrix. Sorry, start again. Okay. It's not the identity. I'm multiplying by the identity and I get the original matrix back, right? Okay, so you try one for a 3 by 3. Hopefully that all makes sense. You're going to try this one. Okay. Multiplying 3, -2, and 5. 0, 2, and -3. -1, 4, -2, and you're going to multiply that by the identity matrix, okay? And before we go to do this, I'm going to push pause, you push pause. We'll work it out separately and see what we get. But before we go to do this, because we're multiplying, this is a square matrix, multiply by the identity matrix, what should I get back? The original matrix. Yes. Okay, so I should get back, because I'm doing the identity matrix times the matrix, or in this case, actually, the matrix times the identity matrix, and I'm going to get back the original matrix, right? Okay. So push pause. I'll push pause. We'll see what we get. All right, so I worked it all out, and indeed we do get the original matrix back. I'm not going to do them all, but you can kind of see I tried to color code it. The first row times the first column. Of course, I've got these extra zeros in there, right? Let me try to show you what I got. But whenever I multiply here, the first times the first, 3 times 1, I get a 3. But then the other guys go away because it's 0, 0. So it's 3 plus 0 plus 0, right? And then for this first row, second column, I've got a 0 times the 3. So that goes away. And then 1 times -2 is -2, but the 5 times the 0 will be a 0. And so on and so forth. So 0 plus -2 plus 0. There we go. So you can see I tried to color coordinate it. I did first row, all 3 of the columns. I got this first row back. And then in green, and some of you, I'm sorry, I apologize if you're color coordinate or color blind. This is not a color necessity thing. I'm just trying to color code it if possible to help people out. So second row times first, second, third columns, first, second, third columns. That's this row. And then in purple, I've got the third row times first, second, third, which gives me the third row. Okay. So that's the idea behind whenever I multiply by an identity matrix, I get back the original. So this looks like m times I equals m. Okay. The one I did earlier, sorry, would have been, I did the identity first, right? So I times m still gives me m. So we see this was a 2 by 2. This is a 3 by 3. It doesn't matter. Either one can come first because They're square matrices. That's the whole entire point here, right? They're square matrices. All right. So with that in mind, my next example should be like, you can't fool me, Dr. Webster. Should be pretty straightforward. So it's 1 0 0 1. Okay. That's the matrix identity for a 2 by 2, right? We're okay with that. But it says times, and it's 2, -1 3, -2 0 4. And I hope that you're looking at it going, no way, no way, no way. Okay, 2 by 2 and a 2 by 3, that would actually be okay, right? As far as being able to multiply it out. But the problem is, I'm not going to get back what I need, what I want to be getting back. Okay. So, which for purposes of this particular section of material is a square matrix. Okay. Whenever I multiply it out, I'm going to get a 2 by 3. Okay. I'll even get, looks like I'm going to get the same thing back. That's okay. But the problem is, this is a 2 by 3, right? Okay, so this is not going to work out for me as far as having square matrices. Okay. All right. So then the question becomes, oh, hang on. Let me show you real quickly the opposite of that. So if I had flipped that and put the matrix first, 2, -1 3, -2 0 4. Now I've got a 2 by 3 first. If I was going to multiply it, I'm sorry, here we go. Running out of space. If I was going to multiply it, could I multiply it by that 2 by 2 again? No. I would have to multiply it by what? Because it's a 3, I'd need the 3 by 3, right? So with this guy in the front, it was the same matrix, but whenever the identity matrix was first, in order to be able to multiply it, I had to have a 2 first because the row or columns here has to be the rows here, right? But for this one, in order for me to be able to multiply here, it has to be a 3 by 3 as my identity matrix. Now, when I do the multiplication, I'm still going to get a 2 by 3, so that's okay. Okay, this is very doable. I can do the multiplication, but the problem is this guy going to be square? No, that's not a square. Not a square matrix. Okay. So again, we're going to be dealing primarily with a square matrix times a square matrix. All right. So let's do one more because I want to show you, well, I guess at least one more. I want to show you what this is going to look like. So let's say that we have 7, 2, -32, and -9 times -9, -2, 32, and 7. And the directions say, are these inverses? Oh, well, we haven't talked about that quite yet. Not like that. Okay. So are these inverses? Okay. So if this is my original matrix, here's my M, then what they're saying is this could be, might be the inverse. And they want me to find out if it's true or not. Is that the inverse? Well, how do I find that out? Okay, let's go back to what we talked about earlier. The original thing, which in this case is going to be a matrix, times the inverse would give me back what? Oh, excuse me, the identity, right? It's going to give me back the identity if this is an inverse. Ah, that's right. Okay. If you multiply M times, and I'm going to call it INV, you get back the identity. Okay. So earlier, M times I gave me back the M, But here, if this is indeed the inverse, I'm going to get back the identity. And in this time, these are what? 2 by 2. And this is a 2 by 2. I can indeed legally multiply those, so I'm good. And what do I get back left back over? A 2 by 2. And indeed, I do have a 2 by 2 identity matrix. So if these are inverses, when I'm done, put that off to the side. And when I finish multiplying these, if these are inverses, I'll get 1, 0, 0, 1. Okay, so let's do that together. I want to make sure everybody has a chance to do all this math. I'm going to do first row, first column. Okay, let's be careful. I'm going to actually write this out because there's a lot going on here. Okay, so I've got 7 times negative 9. And I know that 7 times 9 is a 63, right? But it's negative in this case. Okay. And then plus, I'm going to add these two together. And I've got 2 times 32. Well, that's a 64. Okay. So I'm going to do that math. That's going to be my first row, first column. All right. Set first row, second column right here. 7 times negative 2. Well, that's negative 14 plus, and then it's 2 times 7. That's a positive 14. I'll do that arithmetic in a second, but that's going to be the element that's in the first row, second column position. Okay. So sometimes there's a little bit more arithmetic involved in these, and I don't just go straight to the answer. Okay. I try to figure it out. Okay. So here I've got, now this is interesting, negative 32 times negative 9. Well, negative and negative is a positive. Okay. 32 times 9, I don't know what that is, but I would make the argument I don't even have to know what that is because here I see a negative of that. So just negative times a positive. And whatever that number is, here it's a positive, here it's a negative, and I know those are going to add out. Let's go ahead and get the number, but I'm like, okay, this is nice. 32 times 9 is 288. Okay. So here, when I multiply, I'm sorry, where was I? Here. I'm on the second row, but I didn't change colors. Okay, so second row times first column. Negative 32 times negative 9 is a positive 288. And negative 9 times positive 32 is negative 288. That's what I was saying. One's a positive, one's a negative. That's going to become 0, which is good. And then second row, second column, here we go. It's a positive because negative times negative is positive, 64. And negative 9 times 7, I already said that's 63, right? Okay. And hopefully you're kind of seeing this, but just in case, let's go ahead and do the arithmetic. Okay, negative 63 plus 64, that's a 1. Negative 14 and 14, that's a 0. 288 minus 288, that's a 0. Those are actually additive inverses, right? 64 minus 63, that's a 1. Is that the identity matrix? Question mark. And the answer is yes. Okay. So remember the idea here. Let me scoot back down just a tiny bit. Okay. The idea here is you wanted to know, are they inverses? And the way you know is you take them, you multiply. This is my original matrix. This is my inverse matrix. And if I get back the identity matrix, which I did, then these are indeed inverses. So are they inverses? And the answer is yes. Of course they are. We knew that. All right, so that's what's up there. Okay. Let's see what we got. I'm going to give you the notation for this inverse matrix because I didn't give you that yet. Just so we can see it because it's going to be in your homework. An inverse of M, an inverse matrix, of m is noted as m raised to the negative 1 power. We call that M inverse, okay? The inverse of that particular matrix is what we're looking at, okay? So what we're saying here, whenever we use this little property here, we said whenever I multiply these together, I get back an inverse or an identity. The math looks like M times M inverse, okay? Or we could switch the order, M inverse times M. I can only do this because they are squares, right? In this case, up here, they were 2 by 2s, but because they're square matrices, I can switch the order when I multiply, and I'm okay. And whatever I do, no matter which order I give them, I get back the identity. So this gives back identity matrix. That's what we're saying. Okay. So if I multiply the m and its inverse, I will get back the identity. All right. That's what we're talking about. So let's try it and see what we got. I'm going to give you an example. All right. I've got an m, 3, 2, 1, 2. And I don't, oh, sorry, there we go. I don't know what the inverse is. M inverse is, we're going to call it A, B, C, D. So what we're going to have to do is we're going to have to figure out what the A, what the B, what the C, what the D are. Okay. We're going to find all of those. So how do I do that? Remember, we just said it. Okay. The M times the M inverse is going to get me back the identity. Okay. And these are both 2 by 2, so I can do this, right? Okay. So here we go. The M guy, 3, 2, 1, 2, times the M inverse guy, A, B, C, D, is equal to the identity. And in this case, it's a 2 by 2 matrix. So that's a 1, 0, 0, 1. If these were 3 by 3 matrices, then sure enough, you would use the 3 by 3 identity matrix, right? So absolutely, you could do that. So how's this going to look? Let's do it. Okay. We're going to say, for right now, we're going to leave this right-hand side alone. And we're going to say, let's multiply these two matrices together. We can do that. We know how. It's going to look a little weird at first, but we can do it. First row times first column. So that's going to be 3 times A plus 2 times C, right? And then first row times second column, that's going to be 3 times B plus 2 times D. Okay. Second row times the first column, that's going to be 1 times A plus 2 times C. And then last but not least, second row, second column, it's going to go right here in this position. 1 times B plus 2 times D. Okay. And whatever that stuff is, we don't know yet, but we'll figure it out in a minute. It's going to be equal to 1001. Okay. So here's what you're going to do. And this is kind of an interesting situation. In this case, we're starting out with matrices, but look at this. I've got, let me scoot up a little bit. I've got all this stuff. Okay. And this is by the way, this is a 2 by 2 over here. And this is a 2 by 2 over here. And they're set equal to each other. So I've got 2 by 2 matrix equals a 2 by 2 matrix. And so what I know is the guy in the first row, first column here is equal to the guy in the first row, first column there. Does everybody agree with that? They're in the corresponding positions, first row, first column. So there's an equal sign. They must be equal. So what I've got here is a little equation. 3a plus 2c equals 1. And what's going to happen is we're going to end up with 4 of these little equations, and it's going to be really pretty cool. Okay, so it's going to work out pretty cool for me. In fact, you're going to see some interesting stuff happen here. So give me a second. All right. First row, second column. Let's get that guy together. 3b plus 2d equals 0. Does everybody see it? That guy equals 0. I got an equation out of that. The second row, second row, first column. Okay, I've got a 1a plus 2c equals 0. Those are equal. And then last but not least, I've got this guy has to be equal to that guy, right? So second row, second column. 1b plus 2d equal 1. Okay. So what I've got here is a system of equations with 4 equations in it. Okay. But if I look, excuse me, if I look, oh my goodness, really closely, this first equation has an A and a C, and this third equation has an A and a C, but the other 2 don't. And in fact, the other 2 have a B and a D, and the first and third don't. So actually what I've got here is 2 little systems of equations, which is kind of cool. Okay, so I'm going to pull out this guy first. I'm going to pull out, did I write that wrong? Hang on a second. I'm sorry, give me just a second to make sure my math is working out okay. Okay, sorry about that. There's actually an error in my notes. I just got it. Okay, so I'm very sure that what I've got here is right. So, because I came back 3 times A, 2 times C, 3 times A, 2 times C. Yep. Okay, so here's my systems of equations that I've got. I've got 3A plus 2C equals 1, and I've got an A plus 2C equals 0. Okay. And I think that I can, so interesting. I just in my notes, the variables are completely wrong, basically. I'm sorry about that. It's just freaking me out. Okay, so an A and a C. I think I can solve this system of equations just the good old-fashioned way, or I can stick it back into a matrix, however you want to do it. Okay. And then these 2, those have the same equations, so or same variables. So 3b plus 2d equals 0, or 1b plus 2d equals 1. Okay, so either one of those or both of those equations, I like them, and we can totally solve them and figure it out. If you want to, you can stick this back into a matrix and solve it. I guess I should do that way just so that we can get a little bit of practice with solving systems of linear equations with matrices. So let's remember how to do that. It's a 3, 2, 1, and a 1, 2, 0. Okay, because I'm coming from here 3, 2, 1, 1, 2, 0. And this is no longer a square because I've got this augmented matrix back here. But let's see what we get. I'm going to flip these guys, switch my rows. 1, 2, 0. 3, 2, 1. And then I've got the 1 there. So what can I multiply it by to add down? And I'm going to multiply by -3. Okay, so I'm not changing the top row. 1, 2, 0. Okay, -3 times 1 is -3 plus 3. That's my 0. That's what I'm after. -3 times 2 is -6 plus 2 is a -4. -4, yep. And -3 times 0 is 0 plus 1 is a 1. Okay. So now I've got the 1 there that I want. And my next thing I want is this guy to be a 1, and it's a -4. So I think I can multiply that by -1/4, and I'll be okay. Again, I'm leaving the top row alone because he's fine the way he is right now. 0 times 1/4 is 0. -4 times -1/4 is a 1. And then -1/4 times 1 is -1/4. Okay. And last but not least, I need a 0 right here. So I'm going to, let's see, what can I do? I'm going to multiply this second row by a -2 and add it up. Okay. And I'm not changing the second row at all. So I am going to um, leave it like that. Okay. Rewrite it. So 0 times -2 is -2 plus, or 0 plus 1 is the 1. That doesn't change. -2 times 1 is the -2. Plus 2 is the 0. That's what I wanted. Be careful here. -2 times -1/4. That's going to be a positive. 2 divided by 4 is 1/2. Plus a 0 is a 1/2. All right. So I can solve these equations like that. So now I know, okay, what was this? This was my A column. This was my C column, right? So A, C, and that's my number. A equals 1/2. Okay. C equals -1/4. All right. So we can totally solve these systems of equations like that. We have this other system of equations right here. I would like for you to go ahead and work that one out and see what you get. I'm going to push pause. You should push pause. I'm going to put it into a matrix. We're going to see what happens, and then we'll get our answer out. Okay. So see what you get. Thanks. All righty. I've worked through mine, and I think I've got my answers here. Hopefully I didn't make any silly little arithmetic mistakes. But if you want to pause and look at my answers and make sure yours works okay. The one thing I did here is, ooh, let me make sure I did this right. Hang on just a second. All right, I might have mixed this up right here at the end. Hang on a minute. Okay, so I worked through, got my 1, got my 0, got my 1 here by multiplying by -1/4. That works. And then to get the 0 here, I'm adding. So I did -2 times 0 is 0, plus 1 is 1. -2 times 1 is -2 plus 2. That gives me the 0. That's what I'm after. I didn't finish this process is what I didn't do. Okay, -2 times 3/4. I did that math right here. -2 times 3/4 is -6/4 or -3/2. But then I forgot to add that to the 1. So let me change that real quickly right here. Okay, so -3/2 plus a 1 that was up there, and with a 2 on the bottom, that'll be 2 over 2. That's going to be -1/2, right? Subtract the tops, keep the denominator the same. So -1/2 right there in that spot, which means that my B is a -1/2. All right, I didn't quite finish my process. The D here reads very easily as a 3/4. All right, so hopefully we got there, no issues. Push pause, go back and look at my solution, make sure your solution works the same. That'll be just fine. All right, so some of the examples are going to ask you to check. Okay, so this says, are these inverses? Okay, the way you will know is because you will go ahead and multiply them out. 2, -3, -1/2, 2 is the first, and the second is 2, 3, 1, 2. And you will multiply them out, and what should you get whenever you're finished? The identity. Yep. 2 by 2, 2 by 2. These are squares. I get the square inverse. So you can check it and see. So do that real quickly and let's see. Okay, I think I've got, whenever I do the first row, first column, I've got a 4 plus a -3, that's a 1. First row, second column, I've got a 6 minus a 6, that's a 0. Second row, first column, I've got a -2 plus a 2, that's a 0. And second row, second column, -3 plus 4, sure enough, that's a 1. So you're going to be able to check these pretty easily normally, especially if it's a 2 by 2, and see whether or not you end up with the identity matrix coming back. All right. So the other thing you can do if you're trying to find an inverse of a matrix, okay, is we know this guy right here, m times m inverse equals the identity. What happens is you could solve this with three systems of equations separately. You can make sure that the first one you multiply and get the first row, or yeah, first column of the identity matrix. But they found out a while back, a long time ago, they figured out that, hey, what I can do instead of trying to work it around until I get to the inverse is I can do this. Okay. It's going to be an augmented matrix, but instead of augmenting on the solution, I'm going to augment on the identity matrix. So here's what it's going to look like. Okay, if I have, I'm going to start with a 2 by 2, 4, -6, I'm sorry, 4, -1, -6, 2. Okay, and I want to figure out its inverse, then I can make an augmented matrix that looks like this. 4, -1, 6, 2. That's my original square matrix, right? And again, got to be square. Okay. And I can augment onto the back of it the identity. Okay. So this ends up being M augmented with identity. Okay. We've seen that with just the solution set at the back, but we haven't seen it where we've got the identity matrix in the back. Okay. So what are we talking about here? Well, what we're talking about now is, and there's a statement, so let me write it down. Okay. To find the inverse matrix, we're going to call it M with a -1 as the exponent. Okay. We will transform M augmented with I into I augmented with some other matrix. We'll figure out what it would be. Okay. And then if B exists, because sometimes these things don't work out right. Okay. If B exists, then it is the inverse of M, and we're going to again call it M inverse. Okay. So as long as the M is a square matrix and all that good stuff. So this works for square matrices. Okay. And something to keep in mind here, and we haven't talked about this yet, but you got to be careful, because if I had a matrix full of zeros, for instance, or if I had even an entire row here of zeros, then whenever I went to go multiply this, I'd get 0, 0, 0, 0, right? Kind of thing. So you have to be careful that you're not like completely getting rid of any matrix to work with. So there are probably some examples in your homework where I know there are, because I saw them. There are some examples in your homework where you've got too many zeros going on, basically, and so it's not going to work out for you. So be careful, because then you'll be like, oh, I can't get where I want to be. So I want to transform this guy into the inverse, augmented with some other matrix, and we'll see what that looks like. So let me pull this guy down. So I'll have plenty of room to work on him. 4, -1, 6, 2, and he's augmented with 1, 0, 0, 1. Okay. And I want to make that into the identity. Did I say inverse a minute ago? I hope I didn't. I'm sorry. Too many I words. I want to make this look like the identity, which is what we were doing before when we were solving systems of equations, right? Make this a 1, make this a 0, make this a 1, make this a 0, and do it in that counterclockwise motion, right? 1, 0, 0. I'm sorry. 1, 0, 1, 0. Okay. So do that. And as I do that, this side over here will automatically change because it's dependent on what I'm doing on the left. And I'll end up with some other matrix over here on the right hand side. I'll end up with something that'll be my B. And if it's existing for me, hey, this is great. It's a matrix, or it's our inverse. Okay. So let's do what we do best here. Let's make that guy into a 1. How am I going to do it? I think I'm going to multiply him by 1/4. Does everybody agree? 1/4 times 4, sure enough, that's a 1. Unfortunately, 1/4 times -1 is a -1/4, but that's okay. We'll be all right. 1/4 times 1 is a positive 1/4, and 1/4 times 0 is still a 0. We don't care about him. Okay. Did I do anything to the second row? Nope. So I'm going to just rewrite him. 6201. I know these take up a lot of paper, but sometimes you save yourself heartache and mistakes if you will rewrite that. Okay. Now I've got the 1 here that I want, so I'm just going to rewrite the first row because I want to make this guy a 0, right? So I'm not changing the first row. Go ahead and rewrite it so that you don't mix it up later. Okay, leave him alone. What can I do here to make this 6 become a 0? In my head, I hear you say, multiply by -6 and add it down. And that would be correct. -6 times 1 would be -6 plus 6 would be a 0. Be careful. Go off to the side if you need to. Here, I'll do my arithmetic over here. -6 times -1/4, right? A negative and a negative is going to be a positive. And 6/4 is going to be 3/2. I did that one just a little bit ago. Okay, so this is going to be 3/2. And then 3/2 plus 2. Well, 2 is the same as 4/2. So I think this is 7/2. Okay. Okay. So multiplied that. I added the 2. I'm good there. -6 times positive 1/4. Well, that's a -3/2. And fortunately, I'm adding it to a 0. So that's just -3/2. And then one more. -6 times 0 is 0 plus a 1 is just a 1. Okay. So you can see how as I go along, these numbers over here are changing from the original identity matrix to something else, right? So, and that's exactly what we would want to happen. Okay, next, I need this guy to be a 1. Okay, what can I multiply by to make 7/2 equal 1? And in my head, I hear 2 7s, and sure enough, that would be correct. Excuse me, I am not changing the top row, so I'm just going to rewrite it. Okay, this guy times 0 is just 0. 2 sevenths times 7/2 is a 1. Those are inverses, by the way. If you notice, I did that multiplication. I got the identity back. Okay, so for the multiplicative identity. I think I'm going to have to do this arithmetic to the side. 2 sevenths times -3/2, -3 sevenths. Okay, and then 2 sevenths times a 1 is 2 sevenths. Okay. So, we don't love the way that's looking with a lot of fractions in it, but it's okay. They're not horrible fractions. And last but not least, I want this guy to be a 0. Whenever I'm trying to get zeros, Oh, excuse me. Do the multiply by some number and then add. What can I multiply 1 by to get to? It's the inverse of -1/4. I think I need to multiply by a 1/4 and add it up, right? Okay. So the bottom row is not going to change. I'm going to go ahead and write that down so that it looks the same. 0 times 1/4 is 0. That's a 1. 1/4 times 1, that's a 1/4. Plus a -1/4, that's a 0. I'm going to have to do this math to the side. It's okay. Keep you some scratch paper. 1/4 times -3/7 is a -1, or 1 times -3 is -3. 4 times 7 is 28. Okay. So that's a -3 over 28. And last but not least, 1/4 times 2/7. I'm going to go ahead and reduce that. 2 goes into 4 once. That's a 1 over 14. Okay. So 1 over 14. I'm adding it up to the 0. It's just a 1 over 14. Okay. So I've got an answer there. I do not have my answer in my paperwork, so I don't know if it's right or wrong, but I have an answer. We're going to go with it's right. If it's not, I made some silly mistake on my arithmetic. But here, this would be the B. This is my identity, right? So I've got I, identity, augmented with the B, and this matrix is okay. It exists, right? So as long as I did my math right, there's my inverse. Okay. Because I remember the word I used, transform it. It looked like this. This was M with the identity, right? Okay. Transform M with the identity into I with some other matrix. There it is. And as long as you can do that, as long as the answers come out right, which, what do I mean by that? Like if I had a 0, 0 down here, I'd be in trouble, right? Because things would go away. But that matrix is a good matrix. And as long as I've got a matrix that exists, then I have found my inverse, which is awesome. Okay. All right. Um, I have an example that's a 3 by 3, but honestly, I don't want to do it. So I'm just going to leave that for you guys to do to make sure we're okay. Have I done this one? Let me check my math really quickly. Yep, I did that one. Okay, I think that short of doing inverse matrices, we are good to go. I'm sorry, inverse matrices of a 3 by 3, and I just don't want to get into it because this video is starting to get long. It's the same exact process. Okay, you would augment the matrix with the identity and then do your row operations until you get the identity with the B. And if that B is good, then you have an inverse. All right. So short of doing that, I feel like we are good to go. So I am going to stop this and let you work on your homework. Let me know if you have questions.